Let's look at a two-dimensional collision. Here I have objects A and B. A has a mass of 10 kilograms, B has a mass of 20 kilograms. Their initial velocities are 60 degrees to the horizontal and 30 degrees to the horizontal, respectively. And they're going to come together, they're going to collide, and they're going to stick together after the collision and be moving to the right at 5 meters per second. So to solve this problem, we have to use the law of conservation of momentum. And that has to apply, because momentum is a vector, that has to be true for both the x and the y. So both horizontally and vertically, momentum has to be conserved. So in this case, if I start with the x, that's telling me that I've got the total initial momentum in the x has to equal the total final momentum in the x. And initially, I have two objects that have some x momentum, A and B. So the momentum of A is, at least in the x direction, is ma times va initial x. Then I have to take into account B's, vb initial x. And these guys stick together, so that's ma plus mb v final. V final x. Okay, so that's the law of conservation of momentum as it applies to the x direction. Now we have values. We can go ahead and stick those values in. Now bear in mind, this is the x component of the velocities that we're dealing with, so we're going to have to do a little vector analysis. To begin with, I know the mass of A is 10 kilograms. And then I only want the x component of the velocity, so I need to take the magnitude. So this is the mass, so I put parentheses around it. Now I'm going to do the velocity. I'm going to take the magnitude, which is just, I'm just going to call it VA. It's obviously the initial momentum at VA, and then since this angle, I want the x component, and since the angle is relative to the horizontal, that's going to be the cosine of 60 degrees. Now then I'm going to go through and do B, same idea. B though has a mass of 20 kilograms, and I'm going to take its velocity VB, and again it's going to be a cosine function to get the x component. This time it's going to be cosine of 30. And then over here, 10 plus 20, I'm adding the masses together. 10 plus 20 is 30, and then 30 times 5, that's going to be 150. And so I can do a little bit more here. The cosine of 60 is 1/2, so this becomes just 5 times VA plus cosine of 30 is the square root of 3 over 2, so this becomes 10 times the square root of 3 times V sub B. Again, cosine of 30, square root of 3 over 2, 20 divided by 2 is going to give me the 10, and then it's going to be multiplied by that square root of 3. Okay, so here's my formula that I've reduced it down to. I have two unknowns, so can't solve it yet. I need another equation, and that's going to come from the y momentum. So we're going to do law of conservation of momentum, but we're going to apply it to the y direction. So that's going to mean P initial y has to equal P final y. Now to begin with, in the beginning, once again we have A and B, so it's going to be the mass of A times VA initial y plus mass of B, VB initial y, and at the end there is no y momentum, so this all has to equal 0. So put in what we know. This is going to be 10 times, I'm going to have VA. This time I want the y component of the velocity, so that's going to be the sine of 60 plus 20 times VB sine of 30, and that all has to equal 0. Ten times the sine of 60. Sine of 60 is root 3 over 2. So this is going to become 5 times root 3 VA, okay, plus sine of 30 is 1/2. So this is just going to become 10 VB equals 0. And what I have here are two equations with two unknowns. I have made a small mistake here. Let me go ahead and fix that. My mistake is I forgot to recognize that the y momentum, the initial y momentum of A, is going down. So there should be a minus sign here. So let me fix this. There should be a minus sign right there. And that again is because the y component of the velocity is going to be negative. So this really came from the y component of velocity. That has to be negative. And that's why I'll be adding this negative quantity to this positive quantity to get 0. And now, as I was saying, all we have to do is solve for one of the unknowns in terms of the other, and then substitute it to get the answers. Here, I'm going to do it down here. Well, actually, as I look at it, this would be the easier one to do. So we can easily solve for VB. We're going to have 10 VB equals 5 root 3 VA divided by 10. And VB is going to equal root 3 over 2 times VA. And now all I have to do is take that and substitute it over here and then solve for VA. So if I do that, this is going to be 5 VA plus 10 root 3. VB is root 3 over 2 times VA. That has to equal 150. Okay. So root 3 times root 3 is just 3. 10 divided by 2 is 5, so it's going to be 5 times 3, that's going to be 15. So this is going to be 15 plus 5, so that's going to give me 20 VA equals 150, and VA, this is 7.5 meters per second. Take that, plug it up here, and you get that VB equals approximately 6.495 meters per second. This is the approach for solving a two-dimensional collision. You're still using conservation of momentum. You got to look at the x direction, you got to look at the y direction. Momentum has to be conserved, so you have to count for everything that has x momentum, and then you have to count for everything that has y momentum. You need to pay attention to your components, whether they're positive or negative. As I almost forgot to do here, remember that the initial y velocity of A is negative because it's going down. I'm calling it up positive, so since there's a downward motion to it, that's where that minus sign came from. But this is the idea, and this is the general approach for any 2D collision.